So, hello everyone. Thanks for being here. Today in this session, we will be speaking about how Amadeus uses MongoDB in order to scale our platforms in the NDC ecosystem. So joining me on stage will be Nicolas Benhamou, who is Advisory Solution Architect at MongoDB, and myself, I'm NoSQL expert at Amadeus.
The best one.
So if you already work in Sofia Antipolis, there's a great chance that you have already heard of Amadeus. If not, then it's most likely that you have already used some of our services, even just for coming for this conference today. Amadeus is a major player in the travel industry. We provide IT solutions for airports, airlines, travel agencies, hotels, and many more. Just to give you an idea about the order of magnitude that we work with, in 2024, we have supported more than 400 airlines and handled the boarding of more than 2 billion passengers. All this generates a massive amount of traffic across our systems, and for this, we were able to cross the 150,000 transactions per second threshold. In order to build and operate these systems, Amadeus employs more than 20,000 employees worldwide, which are representing around 150 nationalities. As for myself, I am part of the travel search and reservation platform. This platform actually covers the entire journey from the inspiration phase, when you don't know where you want to go, just wondering where you want to go for your next vacations, to the booking, and all the way till boarding the airplane.
Thank you, Ali, for this crystal clear explanation. We look so small compared to Amadeus. So I'm Nicolas. I'm a solution architect of MongoDB for 4 years now, working with Ali for almost 3 years on multiple products and projects. So MongoDB, this is basically the most popular NoSQL DB in the world. So by hand, who knows MongoDB in the room? So we're done. That's fine. Everybody knows MongoDB. Yeah, so MongoDB has been downloaded like 32 million times a month, and it's growing. We have 55K customers in the world, which is quite impressive. And currently in Amadeus, we have more than 120 clusters in production, which is not nothing. And today we are going to talk about some of them with Ali regarding the shopping department.
So for the agenda today of this session, first I will set the scene. In the first part, it will be just giving you some context. What is a global distribution system? Why do we need a new distribution capability? What are the challenges that come with the NDC, this new system? And in the second part, it will be a deep dive on one of the solutions that we are putting in place in order to address the challenges while using the capabilities of MongoDB. And so we will be giving some tips and best practices of how to do it. So let's start with the GDS, or the Global Distribution System. In the travel industry, in the early days of travel, if you wanted to book actually a flight, you would have to just call the airlines and wait, sometimes for more than an hour, while agents just flipped through paper files in order to find the next available seat. However, today the situation is really different. So from one side, we have the airline IT system where we store all the offers and the flight inventories. And from the other side, we have travel sellers, such as online travel agencies, meta search platforms, corporate booking tools. All of them would like to have access, reliable and fast access into the booking systems of the airlines. As a global distribution system, Amadeus is just in the middle. So we act as a bridge between the airline system and the travel sellers. We actually aggregate content, we provide real-time access, and we make it easy for travel sellers in order to compare and to book flights across hundreds of airlines, all in one place. However, the situation is a bit different. Now that the way people are shopping for travel, it's really evolving. So for travelers, it's not, they would like to have something more than just a ticket. They are expecting the offers that to be actually personalized and to be actually made for them. And this is where the NDC or the new distribution capabilities come in. NDC would give for airlines more control on the content they are distributing. Actually, they are able to present more personalized and flexible offers. So for example, if I want to travel with my partner, I would like, if it's for leisure, then I would like to have a couple of seats, a package which is including a couple of seats that are placed beside each other, and a checked-in baggage. However, if I'm traveling for work, I would actually like to see more flexible offers and maybe some lounge access. So with NDC, this is possible. On top of this, NDC actually allows, it changes the way that travel sellers are accessing the content. So it's not anymore using the traditional GDS channels, but they can directly connect to the airline APIs in order to access more dynamic and more flexible offers. This way they are able to combine flights with some additional services, such as hotel deals or insurances. So it's really improving the way that the booking feels. So it's not anymore generic, it's a bit more personal for now. However, with NDC, we will have more and more challenges, especially around traffic and system overloads. So just before the NDC world, all the GDS platforms actually acted as shields. We actually optimize the traffic, we cache, we filter out a lot of traffic. So instead of all these thousands of searches of operations arrive to the airline system, there's only 10% of this traffic that directly hits the airlines. However, with the NDC world, the story is totally different. All the search that are coming from the NDC, from the travel sellers, are actually directly hitting the airline systems. And this is a big problem for airlines. So what does this particularly mean? So airlines, they actually have their systems to protect. They would like to really emphasize on the traffic that is arriving from all the travel sellers, from all the aggregators, and they have to actually block the traffic. So in order to protect their systems from overloading, they are imposing some limitations on travel sellers. What they are doing, they would like to limit the maximum number of transactions they are receiving, and in addition, they are putting some limitations where for a given set of shopping requests, there should be a booking just behind. This is what we call a look-to-book ratio. So the challenge that we have here, it's clear. From an airline perspective, they need to protect their systems. However, from the travel seller point of view, they would like to have access to all the NDC content at a high scale and high throughput. And that's why they would like to support use cases such as price comparison or even flight exploration. Solving this is not only by adding more infrastructure, but it's actually by finding the balance between the two sides. And this is where Amadeus actually comes in. Amadeus in the NDC system, it's right in the middle. We have multiple roles in the NDC world. We act as an airline NDC provider. So we actually work with more than 35 airlines in order to support them, to work with them, to help them distribute their content and manage their content, the NDC content. And from the other side, we are still a content aggregator. So what we actually do, we provide for travel sellers the access on all the data that they need all in one place. So not only NDC content, but also low traffic carriers, hotels, insurances, and so on. So our objective, it's really to provide access to travel sellers at high throughput, at very fast access, and still playing with the limitation and accepting the limitation that the airlines have put into place. And how we are doing this, we are actually implementing multiple solutions. So we are working on traffic management from one side, and from the other side, we are working on delivering some new sources of content, of NDC content. And one of the solutions that we have put in place is the intelligent caching, which we will be discussing in details in the second part. So the idea of intelligent caching is actually we want to provide a new source of data, but it's very important to actually keep the quality in a good, at a good level. We have all been there where we are searching for something, for a flight, and then when we click in order to reserve this flight, the price either jumps up or it would just, there's no more availability, and it's really frustrating. So with that, we know that a simple cache would not do it. We want something really smarter, and it's able to provide a quality that is equivalent to the NDC content or to the NDC call. So the offers that the traveler would see would actually be bookable and be valid. So how we do this, I will just give here a small architectural view of the design that we have put in place. The first one, so we will receive a shopping request from a travel seller. Our search orchestrator will handle this request. And then let's assume for now that our cache is fully empty. So what we will do is we'll actually forward this request to the external NDC providers in order to get fresh content from the airlines. The results that we could get back will be actually packaged and pushed inside a Kafka cluster. They will be streamed there. From the other side, we have our microservice, which is the updater that would consume the content from Kafka, but in order to store it inside our cache. But before storing it inside our cache, we need to know for how long this data will remain valid inside the cache. For that, we have our own big data platform, which would also consume the same content from Kafka. And then our data scientists will use this data in order to build some machine learning models that would help us predict for how long every set of offers would remain valid. So these machine learning models are then exposed through inference services, and the updater will be contacting them in order to fetch all this information. We attach it as metadata inside our cache, and we store it there. So the next time we receive a similar request, so instead of hitting the airline side, the airline systems, we'll be actually using the content that is inside our cache. So for this, we have been using MongoDB in order to store all this information. And the setup that we have currently put in place, we are reaching our objectives, which is more than 20,000 searches per second on the range of really a few milliseconds per request. In order to go into details, sorry, I've been speaking a lot for the functional part. I will leave the place for Nicolas in order to tell us more about what is MongoDB.
Yeah, thank you, Ali, for this explanation. So I guess everyone understood the challenges here about how to achieve this. Basically, not just a simple cache, but something more, let's say, intelligent. But it's time to wake you up. If you want to unlock the rest of the slides, we will have to have a little riddle. So I like to say that MongoDB is a 3D system. And I guess you can guess what are these 3Ds in the room. The first D, document, yeah, because with MongoDB we are storing data not into tables, but into polymorphic documents, let's say in a collection. The second D, distributed, yes, so it's a document distributed system, because we will see that to basically handle availability, especially for disaster recovery or some failure management, we'll have to need multiple nodes. So that's why we always hear about what is a MongoDB cluster. So it's a document distributed system. And the last one, I guess this is the most trivial maybe, but sometimes we forgot that MongoDB is also a database. It's still a database, it's in the name. So we'll see that also with MongoDB you can handle transactions. It's something that some years ago it was more complex to handle, let's say, multi-collection document transactions. With MongoDB you can do that right now. So yeah, this is completely a 3D system, which is a document distributed database. Yeah, so a little bit of detail about what is a replica set. So the distributed, let's say, paradigm of MongoDB is to have at least 3 nodes, so 1 primary and 2 secondaries. So it means in case of failure, you will have an election, and let's say a secondary will become a primary. These secondaries are replicated from the primary, so you are sure you are up to date in terms of data freshness. But most of the time, many development teams forgot that these secondaries can also be used for something else. You pay for 3 servers, so let's use them. You can also use your secondaries to handle reads. So every single time you want to build a query, a read query against the MongoDB cluster, you need to ask yourself the question, do I really need to hit the primary? Maybe not. Maybe the few milliseconds latency you have between the primary and the secondary, it's perfectly fine. Let's say I have a search to do for a trip. Maybe 2 or 3 milliseconds of latency between the primary and secondary is totally fine, so I can also distribute the reads on multiple secondaries. What I can do also, I can add as many secondaries as I want. I can do 10, 20, 50 secondaries if I want. And you can also tag these secondaries for specific purpose. If you want to do specific search queries, analytical queries, that kind of stuff. If you want to push data from MongoDB to any big data BI systems, you can also use these secondaries to do that. You are not forced to crush your primary for every single operation. And we'll see in the next slides that Amadeus is doing that wonderfully. You can also shard a cluster. So it means usually in the, let's say in database paradigm in the last years, we basically used to scale the DB vertically. It means you just have more CPU, more RAM, more storage, but at the end of the day, you are stuck. So what you can do with MongoDB, you can split, partition your cluster into multiple smaller clusters to have, let's say, more primaries. So when you have more primaries, you have also more power to ingest writes operations. And also you will have more secondaries. So it's just not only about vertical scalability, it's also horizontal scalability. And basically it's done like this. You will have, one shard will have its own primary, and every single shard will have also secondaries that you will be allowed to use for reads. And from the application standpoint, it's totally transparent. You can totally request, make a request on the MongoDB cluster which is sharded and non-sharded the same way. Of course, we will see that we have some best practices to communicate to you in case of, especially for reads, because as you can see, between the driver and the shards, you have routers. So of course, if you issue a query with, without the shard key, without the partition key, you take the risk to basically fan out all the shards, do a merge operation, and then fetch back the result to the driver. So we will see that with the NDC design, we basically made a data model and query shapes that are perfectly fit to make, let's say, a straightforward query to the router. So the router is aware of which shards he has to reach to have the best performance.
Yep. So thanks, Nico. For this part, I would like to show how we are using MongoDB in the core of our solution. So in order to do this, we are switching a bit, and we are taking the user perspective, the traveler perspective. So the use case that we have here, we are actually booking a flight between Nice and Florence, which is departing the 9th of July, and then it will be coming back 3 days later. So let's see what happens in the backstage of the background of at our site. So such a query inside our cache, it's actually mapped into one document. Inside this document would have all the flight recommendations that are all grouped together. And since it's one document, then here the access pattern would be a key value. So one query would be represented by one document inside MongoDB. These documents are around 100 kilobytes in our cache, and we could have some collections that are up to 4 billion documents. Let's see how we optimize our access patterns to the database. So on the search traffic side, we actually use a single field index, which is unique, we have it on our document key. This document key, we build it on the application side. So we use some specific fields in order to have a unique representation of the documents inside the database. So such as an origin, a destination, departure date, and stay duration. So this combination would give us a unique representation of the documents in the database. And we speed things up by relying on the single field indexes that are provided by MongoDB. This is allowing us to reach search traffic, which is equivalent to 12,000 searches per second at 3 milliseconds response time. In order to update our caches, so we actually use upsert traffic. And what is upsert? It's a combination of an insert or an update. So if there's no content inside our database, it will be inserted. Otherwise, the content will be just refreshed. It will be updated. In order to optimize our access pattern on the injection traffic, we actually rely a lot on the unordered bucket updates. And a bucket update, it's basically grouping several operations in one command. And this way, we are able to save around 30% of CPU and getting 10 times faster operations. And the most critical part is that we are having 4 times less I/O on the server side. And we are pushing our clusters. We are doing around 24,000 updates per second. For the cleanup of the cluster, we have two ways to clean up the cluster. So we have the application, which decides which documents are not valid anymore and decides to just remove them by delete operations. And we also rely on a native feature from MongoDB, which is the time to live index. So here we build an index on the update time, and any document that has not been updated since more than 5 days, it will be automatically deleted by MongoDB. For the distribution of our data, so we use a lot sharding. As this case, it's a key value access pattern. Then when we rely on the hashed sharding. So we take the same key that we use to inject our traffic, and we hash it, and this will allow us to uniformly distribute all the data over all the available shards that we have inside our cluster. So that's the first way that we use sharding inside our application. One additional tip about data compression. So as you can see that we have all the flight recommendations are inside our document, but we do not index them. So we just return them to the application as they are. So what we have decided, so we don't index them, there's no impact on the search traffic. We decided to compress all this content on the application side. So since our indexes are outside this group of fields, then there will be no impact on the search traffic. We will still be having the same performance, the same throughput. What we gained is we do all the compression on the application side. We use ZSTD, and we gained a lot on the cost of the network transfer. And we have smaller documents now. We passed from 100 kilobytes to 12 kilobytes. That's around 90% of saving almost on the document sizes. And so we are able to fit more documents inside the memory, inside the memory of MongoDB. So we can even improve further our search performance. So one small tip here is, if you enable compression on the application side, it's important to disable the compression on the MongoDB server side so that you don't have any loss in the CPU usage. That's for the first use case.
So Ali just said that he can do better than the native MongoDB compression. Thank you, Ali, for this. No, it's a really interesting pattern, which is called the envelope pattern. Basically, you can have, if you have mainly key value access patterns, you can, instead of persisting an entire document with all the fields, including the field names, including the capacity to index these fields, and if you are sure that this portion of data is updated into a single round-trip operation, and if you never retrieve portion of this particular envelope, you can, let's say, use a specific compression algorithm, put that into a binary field, because in MongoDB you can use binary fields. We will see later that you can also use this type to store vectors, but you can also basically put payloads on that. So it's really up to you to decide, do I really need to compress this manually and push that into a specific binary field, or maybe later I will need to index these particular fields into this payload, so maybe I will better stick to a classic MongoDB document. But it's something you can totally do. If you have key value, that's a huge gain. It's like 90% of space saved. So on 4 billion documents, I'll let you imagine the amount of savings you can do in terms of TCO. Yeah, MongoDB, it's still a DB. We just said that we use a single feed index to retrieve the documents per its ID. We just see that everyone knows what are the index type MongoDB is using, what kind of indexes MongoDB is using. Yeah? Nobody? B-tree indexes. So if you use SQL technologies like Oracle, sorry, my bad, SQL Server, MySQL, it uses B-tree indexes, and MongoDB, it's not different. It uses also B-tree indexes. And what is important with MongoDB, and when you save a document, you can have multiple indexes linked to that write operation. So with MongoDB, you are sure that the indexes will be updated at the same time. You are sure that at every single point in time, your indexes will be in sync with your data, which is quite important in some operational/transactional use cases. And what you can control with MongoDB is also the durability. We explained just earlier that if you have a failure on the primary, you will have an election. As you have a replication between the primary and the secondaries, it can happen that when you have an election, you can lose documents if the secondary is not up to date. But what you can do, you can decide when you issue a write operation to acknowledge this operation as soon as you reach a given condition. And the condition, what we call a write concern, can be a condition of the freshness of the data pushed on the secondary. So usually, we use what we call the majority write concern. So just to say that the driver will acknowledge the write operation as soon as the documents will be persisted, at least on the majority of nodes. So in a 3 nodes replica set, it will be 2 nodes. So at this time, you are sure that even if you have an election, you won't lose anything. Of course, it's fully indexable, so it means you can index fields like the doc key in the previous document, but you can also index fields into arrays, into nested documents. So you are free to make this index evolve over time, and it's up to you to decide what kind of indexes you want to use. It can be single field indexes, it can be compound indexes, so it's really up to you. Yeah, so B-tree indexes. Just one word about the famous TTL indexes Ali is using with NDC. Be careful, because when you create a TTL index on a MongoDB collection on a given date, basically the MongoDB cluster will trigger a cron job. By default, it's every minute, that will parse the index keys and then try to delete the expired documents. It looks really cool because you don't have to do any kind of batches, any kind of additional backend applications to handle that. Deletes are just a nightmare. Yeah, one operation you don't want to do in a DB, it's just deletes. It's just the, let's say, the more impactful operation you can issue against the DB. So if you can offload this to a given internal mechanism, that's fine. But you don't really master the amount of documents this cron job is going to delete every minute. So if you have 1 billion documents expiring at the same time, you will trigger a 1 billion delete mini operation on the cluster. And you don't want that at all, because it will consume your IOPS, it will kill your performance. So usually when you need to handle deletes, you need to ask yourself the questions about the expiration. Is the expiration will be spread over time, or do I risk to have a huge amount of documents that will be expiring at the same time? So sometimes you can mix between TTL indexes and classical batching deletes you do with a classical, let's say, cron job. You put that into any kind of backend infrastructure, and that's fine. Another tips and tricks you should be aware of, it's about partial indexes. MongoDB documents are polymorphic. It means you can have the documents we just seen before. They can have various shapes. You can control that with JSON schema if you want to bring control on the document, on the shape of the documents. But sometimes you can imagine having, let's say, transactions, and depending on the status on the transactions, you can have multiple shapes. You can have fields that are not present, fields that are present, fields that have different types. It's really up to you. what you can do to save space, you can decide to define an index depending on some conditions. For instance, I want to only index some documents that have a status equals active, for instance. So you will save a huge amount of index keys in your index. At the end of the day, it's just savings for RAM, for CPU, for everything. So TTL index, be careful. Partial index, go for it. But sometimes B-tree indexes are not the best way to issue a MongoDB query. So B-tree indexes are really cool to say, I want a document by its key. That's what I want to do, that's fine. Or I want a bunch of documents of orders between two dates having a given status. This is exactly what B-tree indexes are built for. This is just very detailed queries. I want to parse a small amount of keys and I want to retrieve a small amount of documents. You can retrieve many documents, but usually it's really good to do that. That's why key value, it's really a good use case. But sometimes, and it's not sometimes, it's every single time, you have fuzzy search, auto-completion to do, regular expressions, multi-criteria search. You know this famous UI screen for the back office applications when you have a huge amount of parameters or just a search bar and you don't really know the query shapes. So it's really hard to define the proper indexes you want to have on your MongoDB cluster. And if you use regular expression, you will kill the B-tree indexes. It will be basically just suboptimal. So what you can do with MongoDB right now, you can also create search indexes. So every single time, same thing, when you issue a read query, you can ask yourself, is the B-tree indexes the best? Or maybe an Apache Lucene search indexes would be better if I have, for instance, auto-completion like start with, contains, multi-criteria search. It's really something you can leverage to save memory, because search indexes are much, much, much better compared to B-tree indexes to achieve that kind of queries. And which is nice, it's just the exact same syntax. If some of you has already uses Elasticsearch or OpenSearch, this is exactly that. So in that case, I just want to retrieve a list of hotels based on the name, because I have a classic auto-completion use cases, and I want to do also a geolocalization of my hotels. So I want basically to retrieve a list of hotels based on the name and on the geographical position. So that's something you can do very easily and very efficiently thanks to Lucene indexes. It will be much, much better compared to B-tree indexes.
Now, for the second use case that we have, it's a bit more complex use case than the first one, so it's not a key value. Here we want a different approach. You see it mainly on a lot of meta search platforms. Here I want to always search for the cheapest flight between Nice and Florence, but this time I don't have any specific dates. So I want to have a range of dates where I'm basically searching for the cheapest flight for the summer vacation. So between the 1st of July and the end of August, and for a stay between 7 to 10 days. So this is a bit different. Here we leverage the range-based, since we have a lot of date combinations in order to perform the search on top. So it's not anymore a key value use case. And this is what we call open search on our side. As you could imagine, there's a huge number of combinations to pass through. And there's a lot of storage that would be impacted when we are doing such type of queries. So without optimization, this would never reach the level of throughput or of response time that we would like to have. So what we decided first to do is to perform a lot of pre-processing on the application side. So basically, instead of having all the flight recommendations inside our documents, we would only choose the cheapest flight and store it inside the document. This would decrease the document size. So instead of having already 100 kilobyte documents, we go down to 3 kilobyte documents. The second part is actually supporting the access patterns that we have. So our query is to find ranges. We have departure Departure dates and duration, these are ranges, so we decided to use multi-key indexes from MongoDB. And here, we chose, actually there's a specific pattern to follow when you are creating your index. So first, you have the fields that you use to perform an equality or an exact match. In our case, it's origin and destination. This, we put them at the beginning of the index. Then the second part of the index would be what you are using to sort. Here in our case is the price, because we are searching for the cheapest price. And finally, the final part of the index would be the range, the fields that you use to perform your ranges. These are the departure dates, the duration, and any other fields if you use them to range on top. So also, these indexes are pretty performant, and we are arriving at 15,000 searches per second. One additional tip is use explain, which is a function provided by MongoDB. It will give you some more statistics, more knowledge on what is happening on the server side. So you can see how many keys are being scanned inside your index, how many documents are being fetched from disk. This way you can really optimize your search queries and the index that you are creating for it. For the injection traffic, we keep exactly the same approach as the first use case. So we use a lot the unordered bulk on the upsert operations. Here we are even arriving to higher levels. We are reaching really 50,000 updates per second. As for the final part, the data distribution, we use a totally different part. So we don't rely anymore on the hashed shard key, but we use a range shard key. This range shard key really is adapted to what kind of queries we are really using, because our objective is to avoid scatter and gather. So we want only to match documents that are living on one VM. We don't want to have distributed traffic on the cluster. We don't want to move documents, then to sort them on a different machine. This will kill the performance. That's why it's really important to switch from a hashed shard key to a range shard key that is really adapted to your search queries. And be careful when you are choosing your shard key. It should really be part of your queries if you want it to be fully optimized.
Thank you, Ali. Yeah, so the shard keys is not only technical, this is functional. And it's you have one shard key per collection. So it means when you have to decide on a shard key, you really need to study before what are your query patterns. So do I really need a hash shard key? Maybe a range would be better, maybe a zone would be better. So it's something you need to decide. Even if you can refine or change your shard key later, it's always better to have an idea of what are your query patterns before choosing the proper shard key. And the scatter-gather mechanism Ali was talking about is exactly what I explained just earlier with the sharding. When you issue a read query, you want to have in the read query the shard key, because the router will be able to target a single shard for you and not do any merge or any routing consuming operations. So yeah, I was forced to put an AI slide in the deck, so sorry about that, but it's something interesting. We discussed about binary fields earlier. Binary fields are really nice to put compressed data into a MongoDB field, into a document, which is a huge improvement and optimization you can do to have smaller documents, because smaller documents means less RAM, less storage, less everything, so that's fine. But what you can do also is vector search, which is quite interesting. What you can do, you can consume any kind of embedding models you have in-house, then push any piece of data. It can be text, video, sound, any kind of data, get a vector back, and then push that vector into a MongoDB document. And it's really nice to do some use cases like data correlation. So as you can see in the graph, they have some restaurants. So it means in a given vector space, piece of data that are close, I mean semantically, will be also close in terms of distance. So it means it's another way to search your data. It's not based only on tokens and text, but only on the semantic meaning of your data, which is quite interesting. And you can apply an algorithm called KNN for k-nearest neighbors to, based on a vector input, you can retrieve basically the closest vectors nearby. And with MongoDB, it's quite simple. I don't know if it's luck or just like this, but you can have, a vector is just basically a list of numbers, of floating values, and you can just, for instance, capture a change on a given document, call an embedding model through the API, get back the vector, and push the vector into a document. So it means in the same place, you can have a document, which is basically your operational / business entity piece of data. And at the same place, you could have the semantic translation of this data as an embedding, which is basically a vector, which is quite nice. And the beauty of this is that you can index that with the Lucene index. So it means you can store semantic translation of your data into documents, make that live thanks to, we will see later, what we call the MongoDB change streams to update these vectors as soon as the document is evolving. And then you can index that, and then you can do vector search on that without any additional vector specialized DB you could have on top of your existing architecture. And yeah, what I like to do, I like these slides because I promote this a lot. Usually when you have multiple kinds of workloads on your application, you can have basically your classic transactions with real customers. And sometimes you can have side use cases. And what you can do clearly, one of the, let's say, best of breed architecture you can do, you can specialize some nodes to serve only specific purpose, like search. So you can imagine having your MongoDB documents living into some nodes, create some search indexes, for instance, vector search, put these indexes into specialized search nodes, and make these nodes available for some specific use cases. So thanks to this, you avoid any kind of noisy neighborhood, any kind of side effects of having your operational and your search workload at the same place. It's really a matter of decoupled architecture. And another thing also, so Ali did an amazing job to put everything into a single document, thanks to pre-processing, that kind of stuff. Sometimes it's not feasible. The classic use case is, for instance, with one customer you have a bunch of transactions, and then you have to maintain the balance on another collection. So you have, let's say, some money to transfer from an account to another. So you have two collections. You have the transaction collection, and you have the wallet transactions. And if you want to do this in an atomic way, you can rely on MongoDB transactions. And to do that, it's just as simple as that. You start a session, you start a transaction, you make your write operations, and then you commit the transaction. So nothing really different compared to what you used to do with SQL technologies. And basically, we use that a lot. I don't know if some of them knows the outbox pattern, when you do SecureS pattern, when you have to communicate between a DB and a topic. Usually it's easy to do, I have a topic and I want to push these messages into a MongoDB cluster. That's nice. But sometimes what you want to do with MongoDB is what we call the SecureS. So you have a write model optimized for ingesting write operations, and sometimes you have very various read patterns, and you don't want to handle these reads on the same collection because the indexes would be not good, because you need to enrich the data. So what you are going to do, you are going to basically create materialized views. And to do that easily, you rely on what we call the SecureS pattern. So it means you have to rely on persisting something into MongoDB, capturing the change, doing some stuff, maybe enrichment. You can move the model, you can change the model, and you want to save that into a different collection to handle other kind of reads. And what you can use with MongoDB is what we call change streams. And basically, it's about persisting something into MongoDB plus pushing into a topic atomically. This is usually most of the developers are handling that with a simple transaction, like I start a transaction, I push my document into MongoDB, and then in this transaction, I emit the message into Kafka, and that's fine. But nothing guarantees you that the commit will succeed. It can fail, and it will fail at some point. So this is just a nightmare where you have something into MongoDB and not in the Kafka, or something in the Kafka and not in MongoDB. So what you can do with MongoDB, you can use change stream to basically emulate an outbox pattern, capture the changes, push the data into a MongoDB collection or a Kafka topic, and then having retry policies. So you can do this basically in an atomic way, which is not trivial to do.
So coming for the last slide, for the key takeaways. For the functional use case, NDC has introduced a lot of value. So yeah, there's a lot of personalization and rich content for the travelers, but it adds a lot of traffic on the airlines. For that, we had to introduce one of the solutions that we have is the intelligent caching in Amadeus, where we are relying a lot on the capabilities and the functionalities of MongoDB in order to scale our platforms. So we are able to support billions of documents inside our cache, and that's thanks to the different features. We are able to support different access patterns, different models, different ways of distributing the content across our systems. So we have the range sharding, we have the hash sharding, and of course, a lot of work has been done on the design of the indexes. So here we showed only 2 use cases, but we have other open source use cases that are even more complex. And thanks to these functionalities, we are really arriving to our objectives to really support traffic at scale with NDC.
Thank you, Ali. Just some final takeaways. Search indexes. You don't have only B-tree indexes into MongoDB, so you need to be careful about choosing the proper index. Workload isolation, use your secondaries. You pay for your secondaries, so use them. Stream processing, if you want to do CDC, secure RS event sourcing architecture, you have chain streams with MongoDB. And do not forget you have also transactions. If you want to persist documents into multiple collections atomically, you can do it. And I guess we're done. Thank you, Ali. Thank you, everyone.
All.
We have time for questions, if we have some questions. Yep. Ah, mal. Non, 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 en fait, effectivement, c'est une très bonne question. Par exemple, on pourrait avoir le cas suivant. On a une requête et on trouve qu'elle est longue parce qu'elle apparaît dans le query profiler comme slow operation. Et du coup, on prend la requête, on fait un explain, et là, on s'aperçoit effectivement qu'on scanne beaucoup de clés et qu'on retourne peu de documents. Donc, on a un ratio scan de clés, documents retournés qui est nul. Et on se dit, bah, ah oui, effectivement, l'index ne correspond pas, on veut créer un nouvel index. Et on a une collection de 4 milliards de documents. Et justement, le sharding aide à ça, puisque le sharding va venir splitter la collection en plus petites collections, et finalement, on n'aura pas une collection de 4 milliards, mais peut-être, alors Ali exagère un peu parce qu'il fait des clusters de 100 shards, mais on aura plusieurs plus petites collections. Et la création de l'index va se faire en parallèle sur chacun des shards. Donc déjà, on va paralléliser comme ça. C'est aussi pour ça que la... Non. Non, et en plus, quand on va créer un index, on va le faire ce qu'on appelle en background. On va pas le faire en... Alors, dans les versions précédentes de MongoDB, on pouvait choisir une option foreground, c'est-à-dire qu'on prend les 3 nœuds et on crée l'index sur les 3 nœuds en parallèle. Là, effectivement, le CPU, voilà. Et ce que tu peux faire, c'est plutôt, tu prends un nœud secondaire, tu crées l'index sur le nœud secondaire. Enfin, d'ailleurs, tu le sors de la topologie, tu crées l'index, et une fois qu'il est bon, tu le remets dans la topologie. Et par rolling fashion, comme ça, tu vas... Alors, certes, c'est plus long, mais tu vas laisser ton trafic assez tranquille le temps de la création de l'index, qui peut prendre effectivement de longues heures si tu as une collection très grosse ou un index très gros. Mais il y a plein de façons de faire en sorte que ce soit le moins impactant possible, le sharding et la création d'index à background en rolling fashion. Voilà. De rien. Oui.
So for this use case, Mongo was really a good fit for us because, as you can see, we have the range sharding, and not a lot of technologies have the range sharding where we could optimize our traffic patterns and really hit one specific VMs and get this type of performance. So we are getting really at 20,000 operations per second, 2 milliseconds of response time, which is pretty impressive to have a technology like this at a huge number of documents like this. So it was exactly, yeah, exactly. That was the main driver for us, scalability and performance.
Juste le range sharding, en fait, il y a plusieurs façons de faire du sharding avec MongoDB. On peut choisir de prendre un champ, de faire un hash et de répartir de manière un peu random en mode load balancer les documents sur les shards. ce qui est une version, j'ai envie de dire, presque naïve du sharding, mais on peut faire des choses plus évoluées avec du range sharding, où on va dire par exemple, de telle borne à telle borne, je serai dans tel shard, de telle borne à telle borne, je serai dans tel shard, et ça fait de cette façon-là, quand une requête de lecture a, une valeur du range, le routeur saura dans quel shard aller viser. Et ça peut, effectivement, dans certains cas, comme celui qu'on a expliqué, ça peut vraiment être optimal pour les perfs. Et là, oui, on répond, on a des temps de réponse autour de 2-3 millisecondes par read query, ce qui est pas mal. Oui. Oui. Oui, d'ailleurs, c'est ce qu'on. Alors, c'est vrai que c'était pas forcément. Il faut pas attendre le dernier moment, en fait. C'est juste que quand tu fais une opération de rajout de shard, tu vas avoir un rebalancing qui va opérer pour que le nouveau shard puisse récupérer sa part de data. Voilà, donc c'est pour ça que quand on sait qu'on va sharder, déjà on crée un cluster shardé de base avec au moins 2 shards. Ça évite de faire une modification de la topologie qui est complexe. Et rajouter un nouveau shard, ça se fait. Enfin, chez Amadeus, on fait ça. Tu connais aussi peut-être. On fait ça régulièrement. Tu peux partir avec 2 shards et arriver à beaucoup plus de shards plus tard. Il faut juste éviter d'attendre au dernier moment. Parce que si ton cluster est déjà sous pression, parce qu'il lui manque des ressources, et si tu lui imposes une opération de rebalancing à ce moment-là, voilà, ça rajoute de la pression. Après, il y a des moyens de se roteler la charge pendant le moment, de se roteler le balancing, mais c'est des opérations qui sont faisables. Pareil, le fait de changer la shard key, c'est possible aussi. Une shard key, c'est pas seulement un champ, ça peut être comme un index, ça peut être plusieurs champs. Donc on peut venir la refiner, par exemple pour rééquilibrer des ranges, on pourrait dire on rajoute un champ dans la shard key pour rééquilibrer plus correctement les ranges, parce qu'on aime bien avoir des shards à peu près de même taille. Mais clairement oui, alors rajouter des shards, ça se fait facilement. Ce qui se fait moins facilement, c'est supprimer des shards.
Yeah, but also one point on this, if you start a new cluster with a lot of shards, and if you want to activate really a lot of traffic from the beginning, think of pre-sharding and pre-preparing like empty chunks everywhere so that you have less load, because if you start from zero and you don't prepare it in advance, all your update traffic will arrive on one shard, which would break it down. So remember of pre-sharding and pre-preparing all the chunks in advance. That would help a lot.
Yep. You want to elaborate on that?
So this use case, we have really some high constraints on the response time. For this, we don't just let any text search indexes, or we don't rely on queries that don't have any support of indexes behind. And every query that is arriving, every search query that is arriving to our cluster, it's actually designed where there's an index that would exactly fit the query that is arriving, in order to have a few milliseconds of response time. With Elastic, you can have more, rich and various queries if you don't know the query patterns that you have. For this exact use case, it's very important to have really low response times, so we prefer to use technologies like MongoDB for it.
Yep. This is the legend. The legend says that we need to have an amount of memory that should be sufficient to store all the indexes into the memory of a given MongoDB cluster, which is not right at all. But this is totally true that in this particular, MongoDB has an internal caching mechanism, which is called the wire tiger cache, and this is a portion of the memory reserved for let's say, the most frequently accessed documents and the most frequently indexes branches. So MongoDB will handle that for you. So it means MongoDB will evict this cache for you. But, and you're right to mention that you have some metrics into MongoDB that can help you to understand how the eviction mechanism is working, just for you to know that if you have sufficient memory versus the amount of reads you have, and also the amounts of writes you have. Because when you issue a write into MongoDB for performance, you will first push the document into the memory. So it's what we call the dirty cache portion of the cache. And then every minute, the cache will be flushed into the disks. Of course, it's journalized on the disks, just to avoid losing documents if you have a crash in the middle of two checkpoints. But usually, you have to basically monitor two things: the dirty cache, because above a given threshold, your MongoDB cluster will start to evict massively, and the application will start to throttle your queries, and the speed of eviction of the most accessed documents in the memory. So thanks to that, you can size the proper amount of RAM you need. But never you basically take your indexes, say, okay, I have 1 terabyte of indexes, so I need 1 terabyte of RAM. No, it's just not like that. You just need to study first your query patterns, the amount of hot data you have and maybe warm, cold data you have, the amount of indexes you have, the pressure of your writes, and then you will have an idea of how much memory you really need for your workloads.
In this one, actually one cluster, it has hosts around 20 terabytes of data, and we have around 2 terabytes of memory. So we are at a 10% ratio. So not all the data is in the memory. Yep. Indexes for us is important to have them in memory because we have really random access, but yeah, the data is not fully in memory. It's mainly on disk.
Usually 10% is a proper guess to start with, and then you can adapt based on the usage. But 10% is, let's say, the average value we see usually in a MongoDB cluster. Oui, effectivement, si tu as une portion, et ça arrive tout le temps dans les bases de données, tu as souvent une portion de données que tu accèdes fréquemment. Par exemple, alors des fois c'est pas vrai dans l'aérien parce que tu as un PNR, tu peux y accéder de façon très étalée dans le temps, mais souvent tu as une portion de documents qui sont plus souvent accédés que d'autres, et ces documents seront plus souvent par définition en mémoire que les autres. Et après oui, si tu as des use cases où tu as des accès totalement random sur tes documents et tu ne sais pas maîtriser ça, tu auras peut-être besoin de plus de mémoire parce qu'en fait, ce que tu veux, c'est d'avoir... Il y a une métrique qui s'appelle le cache hit ratio, et tu as envie d'avoir 100% de cache hit ratio, en fait. Donc, en fonction de ça, oui, tu peux sizer ta RAM correctement, parce qu'à partir d'un certain seuil, MongoDB va commencer à faire de l'éviction massive, et de l'éviction, ça prend des ressources qui ne seront pas disponibles pour les requêtes à côté. Donc, c'est des choses qui se surveillent, qui se monitorent, et il y a tous les outils pour faire en sorte de faire ça efficacement. Ouais.
Yes, so yeah, at one point in our Erding data center, so our data center, we kept adding machines until we reached like 63 VMs in one cluster. Scalability, Mongo worked. There was no major issues, but the issue was on the operations side. So they want to do maintenance, and maintenance for such a cluster took weeks. So taking out machines, patching, and so on, it took really a lot of weeks to do it. It was a lot of effort. So scalability there, it was a problem. And for that, we have developed on the application side one additional level of data distribution. And then now we are able to support multiple clusters behind the application. So the application will be able to distribute the data on top of the balancing and the sharding of MongoDB. We are balancing our traffic across several clusters of MongoDB, which is implemented on the application side. But then on performance-wise from Mongo, no, there was no major issues on that.
Il n'y a pas de hard limit de la taille d'un shard, d'un nombre de shards. Tu peux vraiment faire aller très loin. Après, effectivement, ça pose un problème côté opération. Après, chez Amadeus, il y a des mécanismes en place qui font qu'on utilise... Parce que normalement, tu as un nœud égale une VM, ou à un conteneur. Chez Amadeus, on fait un petit peu différemment. On colocalise certains process MongoDB sur une même machine pour justement avoir moins de machines à patcher ou à upgrader en cas de tous les patchs sécu, les montées de version de MongoDB par exemple. Donc plus de machines tu as, plus c'est compliqué à opérer, même s'il y a les outils qui sont là pour ça. Mais d'un point de vue théorique, tu pourrais avoir autant de shards que tu voudrais et des shards aussi gros que tu veux. Après, c'est juste une question d'usage et de maintenabilité de la solution. Et effectivement, parfois, c'est mieux d'avoir plusieurs répliques assets plutôt que un cluster shardé de... tu peux avoir, par exemple, j'ai un client qui fait ça et qui a des tenants très différents en taille. Donc, une clé de sharding, elle n'est pas super triviale à trouver parce que tu risques d'avoir des shards qui sont unbalanced. Et ça, c'est possible, mais ce n'est pas ce que tu as envie d'avoir. On a plutôt pris le choix d'avoir un back-end qui, en fonction d'un paramètre, donc le tenant ID, dans les architectures multi-tenant, de te répartir la charge sur plusieurs clusters différents, avec une chaîne de connexion différente. Donc, c'est un peu plus de complexité pour le back-end. Mais pour les opérations, c'est plus sympa parce que c'est des clusters qui sont plus petits à maintenir. C'est un peu le classique monolithe versus service plus petit. Et pareil, si tu as un outage, sur un cluster shardé de 100 shards, bah, tu mets tout ça peut arriver, du coup tout est indisponible parce que ton cluster sera indisponible. Et si tu as plusieurs clusters séparés, c'est aussi une manière de diviser pour mieux régner. Donc c'est une balance performance, opération, praticité.